Everybody, my name is Mr. Delora, and this is your Honors Algebra 1 course content digital lectures. So every chapter and section we are going to have some digital notes that you should grab your note packet, follow along with, complete those notes, jot down any questions that you have as you watch these notes. So before we jump into chapter 1, section 1, it's important for us to just quickly review this familiar acronym, PEMDAS. PEMDAS, you may have learned that or memorized it as Please Excuse My Dear Aunt Sally, or People Eat McDonald's and Suffer. This familiar little acronym just reminded us how to simplify mathematical expressions. They reminded us of the order. We're first going to evaluate any parentheses or grouping symbols like parentheses or square roots or even fraction bars or division bars, I should say. Then we're going to handle any exponents, so anything including a power. Then we're going to look at multiplication and division, and then addition and subtraction. Whoops, I should do a subtraction sign. Now, multiplication and division are written in the same color, and that's because you can actually do division before multiplication. Multiplication and division happen at the same time, but they happen in order of moving from left to right. Same thing is true for addition and subtraction. They're written in the same color, and you handle them at the same time, moving from left to right. So keep in mind that this is when we are simplifying mathematical equations or mathematical expressions. Today's chapter is going to focus on solving, and when we solve mathematical equations for a particular variable, we want to isolate that variable using inverse operations. Now, when we use inverse operations, we move in the inverse order of PEMDAS. So we will undo addition and subtraction, then undo multiplication and division, and then undo exponents and grouping symbols. And that's where we're going to start our chapter 1, section 1 notes. Again, every section is going to be accompanied with a web page that has our key definitions with the blanks filled in there for your notes, and our key concept. Today's key concept is using inverse operations to solve an equation. Okay, it simply says here, two operations that undo each other, such as addition and subtraction, are inverse operations. We use inverse operations to isolate a variable and solve an equation. And that's our key concept that we'll practice today. So in order to do that, we are utilizing these properties of equality. Now, you may have learned properties of equality before, and just keep in mind, properties of equality simply mean that when an equation is in balance, you can perform the same operation to both sides and it will remain balanced. All right, let's try some examples of solving equations and justifying our steps using one of the above properties of equality. Example 1a says x minus 9 is equal to negative 12. Solve for x. So some value minus 9 is equal to negative 12. In order to find out that value, we use the inverse operation of subtraction, which is addition, to add 9 to both sides. Now I have x minus 9 plus 9. Those add to 0. So I'm left with x is equal to negative 12 plus 9, which is negative 3. To check this, we could substitute negative 3 back into the top equation. Negative 3 minus 9, in fact, is equal to negative 12. So this checks out. And the step that we used is addition property of equality. So we will abbreviate that as POE. Example 1b says 15.6 is equal to some value plus 7.2. To find out what that value is, we'll use the inverse operation of addition, which is subtraction, to move that 7.2 to the other side. Now these will add to 0, and I'll be left with y is equal to 15.6 minus 7.2, which is 8.4. Now the reason why we can do that, or the justification for that step, is the subtraction property of equality. Example 1c, now I have a fraction, z minus 9 halves is equal to 3/4. I'm going to use the inverse operation of subtraction, which is addition. I'm going to add 9 halves to both sides. When I do that, these will add to 0, and I'll be left with z is equal to 3/4 plus 9 halves. You'll remember that you can't add fractions unless you have a common denominator. So we'll change 9 halves to 18/4. All right, so that's an equivalent equation, or I should say it's an equivalent expression, equivalent fraction. And now we can add our numerators. 3 plus 18 is 21/4. And it's okay to leave our answer as a fraction. So z is equal to 21/4. The reason why I can do that, again, is the addition property of equality. In letter D, we have 4 pi plus t is equal to negative 3.7 pi. Pi is just a number. In this case, we're going to kind of just treat it like a variable. All right, so we're going to solve for t by subtracting 4 pi to the other side. Because negative 3.7 also has a pi, we can combine these by just adding those coefficients together. So t is equal to negative 7.7 pi. And the reason why we could do that, again, is the subtraction property of equality. All right, let's try some examples with multiplication and division. Example 2a says 3 times some variable x is equal to negative 12. In order to find out what that variable is, we will undo the multiplication by using the inverse operation of division. Divide both sides by 3, and x is equal to negative 4. Justifying my step is just simply stating the operation I used. That is the division property of equality. All right, 2b says 7 is equal to 1/2 y. 1/2 of y. I'm going to move that 1/2 over to the other side. And now instead of dividing by 1/2, I'm going to multiply by the reciprocal, because 2 times 1/2 results in 1y. Then I'm going to multiply 2 times 7 to give me 14. Now if you don't trust your answer, remember you can always plug it back in. 7 should be equal to 1/2 of y, which we said was 14. That checks out to be true. The operation we used was multiplication, so we're saying that multiplication, property of equality justifies our math there. All right, 2c says 3 pi x is equal to negative 18 pi. We're going to divide both sides by 3 pi. And when we divide 18 pi by 3 pi, pi divided by pi is equal to 1. So they reduce each other to 1, and I'm left with just negative 18 divided by 3, which is equal to negative 6. So our variable x here results in negative 6. And again, the property of equality that justifies that step is the operation of division. So that's the division property of equality. Example 2d says some variable t divided by 4 is equal to negative 3.4. In order to get t by itself, we're going to multiply 4 out of that denominator. So I'm going to multiply 4 to both sides of that equal sign. T is equal to negative 13.6. And again, the property of equality is multiplication. So we'll say multiplication property of equality justifies that solution. All right, let's look at some word problems, because every problem in life that's worth solving is a word problem. And when we take a look at this first one here, we've got a running example of Usain Bolt in 2016. Won the 200-meter dash with a time of 19.78 seconds. Find his average speed to the nearest hundredth of a meter per second. So one familiar formula you might remember is distance equals rate times time. And if we want to find speed here, we want to find his speed over those 200 meters. That's going to be his distance that he traveled. And here's the time that it took him to travel. Then we're going to simply substitute those values in. 200 is equal to rate times time, 19.78. Now in order to get r, the rate or the speed by itself here, we're going to divide over the 19.78. And we take 200 meters and divide it by 19.78 seconds. We will end up with approximately 10.11 meters per second. Now, I didn't show you my calculations here, but you should punch in 200 divided by 19.78 just to confirm that in fact it is 10.11 meters per second. All right, our next example, on January 22nd, 1943, the temperature of Spearfish, South Dakota, fell from 54 degrees down to -4 between 9 a.m. and 9:27 a.m. That's just 7 minutes. How many degrees did the temperature fall? Well, if we're at positive 54 degrees and we fall all the way down here to -4, then we're going to go from 54 to 0, which that's -54 degrees, and then we're going to go another 4 degrees. So it fell a total of 58 degrees over those 7 minutes. Now, if it asked degrees per minute, we could simply take that -58 and divide it by 7. But here, it's good enough to just answer the question, how many degrees did the temperature fall? And for that, it's -58 degrees. All right, our final example for today, a discounted concert ticket is $14.50 less than the original ticket price. You paid $53 for the discounted ticket. What was the original price of the ticket? And it's a good thing to always start off with a variable that gives you what you're looking for here. Okay, so T, we're going to say, is the ticket price, and that's going to be before the discount. All right, so our concert ticket here was $14.50 less than the original price. So we're going to subtract $14.50 from that original price, and that's going to be equal to what we paid, $53. To figure out what the original price is, that's the value of T, we're going to add that $14.50 back over to the other side. And that's going to give us a total of $67.50. That must have been like a Taylor Swift concert. All right, guys, that's it for today. We'll see you tomorrow.